Alright, ladies and gents, we are in lesson 6.3. So this unit is called discrete functions. A continuous function is what we've been dealing with so far. It can be represented by a curve on a graph, a smooth curve, or a line. Discrete function can't be. Either the domain or the range or both is limited to the natural numbers, so it has points on the graph. We've learned about a couple of special ones. We talked about the Fibonacci sequence. We also have learned how to write an exclusive formula. That's a formula that allows us to get any term, the value of any term within the function, within the sequence. And a recursion formula, which allows us to find terms based on the terms that precede it. Today we're talking about Pascal's triangle and expanding binomial powers. So Pascal's triangle is pretty cool. It has lots of little patterns in it. You can see it at the top of page 9. And we're going to start with an investigation. So A, B, C, and D there is just a expansion. So you're going to take that binomial, A plus B to the power of 1, and reduce it, expand it, and simplify it. Not much to do in that one. You just remove the brackets because it's just A plus B. But A plus B squared, you would use FOIL to distribute that. And then C and D are a little bit more challenging, but go ahead and try and distribute each one of those, and then double check on the board to see how you've done. Alright, I have written out the expansion of each of these powers of binomials. And we're going to start looking for some patterns, okay? So what patterns do you see? Without even going into the rest of the investigation, what do you see already in the expansions? So I'm talking about in this side of things. What are some patterns that you see? See a pattern there? Okay, nice. Do you see a pattern here? Okay. What's happening to the powers of A as we move from left to right? They disappear. They go from 2 to 1 to 0. Powers of B go from 0, 1, 2. What about here? 3, 2, 1, 0. Powers of B, 0, 1, 2, 3. In the next row, it's to the power of 4. So the powers of A go 4, 3, 2, 1, 0. Powers of B go 0, 1, 2, 3, 4. What if we were going to have to the power of 5? The powers of A would go 5, 4, 3, 2, 1, 0. Powers of B would go 0, 1, 2, 3, 4, 5. Okay? There's a pattern with the exponents. What about a pattern of the O? We should say this as well. Look at each term and add the exponents within each term. So this has an exponent of 3. This term has exponent, the sum of its exponents is 3. This term has A to the power of 2 and B to the power of 1. The sum of its exponents is 3. The sum of its exponents is 3. The sum of its exponents is 3. What about row 4? The sum of its exponents is 4. The sum of the exponents is 4. 4, 4, 4. Okay? Another pattern. Let's look at the coefficients of each term. In row 1, the coefficients are 1 and 1. In row 2, it goes 1, 2, 1. In row 3, it goes 1, 3, oh, it's already 3 there, sorry. 1, 3, 3, 1. In row 4, 1, 4, 6, 4, 1. So in row 5, I don't know much, but I'm pretty sure that the first coefficient is going to be 1, the next coefficient is going to be 5, and then if I go all the way to the end of the row, I'm not sure what's going to be in between, but it's going to have a 1 at the end and a 5 in from the end. Now, any guesses on how we get the two that are going to be in there? Because, you know, when we expanded this, well, it's a pattern, but 1, 2, 3, 4, 5 terms. We're going to have 6 terms here in the expansion of a plus b to the power of 5. Any ideas how to get the coefficients of those two terms? Ah, nice. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And 1 always on the outside of the pyramid. Okay? So you've made a whole bunch of connections there. We looked at the patterns in the coefficients. And we've looked at the variables in the terms of each expansion and the degree of each term. And it relates to the power of the expansion. And we're going to finish number 3 first, but go ahead. Number 1 says examine the patterns in the coefficients, and then it says how do they relate to the values found in Pascal's triangle. So go ahead and look at the values of all our coefficients. How do they relate to the numbers found in Pascal's triangle? Gavin? We're just looking at the coefficients of the expansion. So the numbers that I did in green. They are the numbers from the triangle. So you could do the coefficients of an expansion a plus b to the power of 6, and using just that diagram at the top, you could do the coefficients of the expansion a plus b to the power of 7. It's in Pascal's triangle. He follows the same pattern. Okay? So, number 3. Predict the terms in the expansion of a plus b to the power of 5 without doing any math. Okay, so we've already got the coefficients. I'm going to let you go ahead and finish it off. You need each term, just like you did in the previous step, the whole expansion. The variables, the exponents, coefficients, everything. Okay, I'll give you a second to do that. One way to do it is to write out your coefficients first, and then just know that you're going to add your variables in there. Again, you could do it the other way. You could do your variables first and then your coefficients, or if you're real quick, you can do it all at the same time. I know my first coefficient is 1, and I'm going to start with a to the power of 5 and b to the power of 0. Now, I don't need b to the power of 0, that's just 1. And I actually don't need to write that coefficient 1, because it's 1 times a to the power of 5 is just a to the power of 5. I'm going to put a plus sign. Now my exponent for my variable a is going to go down from 5 to 4. And now instead of b to the power of 0, I'm going to have b to the power of 1. Now I can add the next term. I know the coefficient is 10 because I looked at Pascal's triangle. And my a variable is going to now be to the power of 3. It's going to go down 1, and the exponent on b is going to go up 1 to 2. Next term, coefficient is 10. The power on a is going to go down 1. B is going to go up 1. And every time I can double check that the sum of exponents within each term is 5. So 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5. I have a to the power of 1, b to the power of 4, plus b to the power of 5. So if you work carefully, pay attention to the patterns, you use Pascal's triangle, it's not too tough to record those things. Okay, in A, we are asked to write the first 7 rows of Pascal's triangle and label the rows. I would do it by not looking at the front. Okay, don't look at the previous page at all. Just try to do it from scratch and do it nice and neatly. Start with 1 at the top and then 1, 1. And from there you can follow the pattern that we did. Basically, you're always going to have 1 on the outside, and then the next term is the sum of the 2 terms above it in the pyramid. Try to do it without looking at the front at all. Leave yourself a good amount of space. And when you get to the row that starts with 1, 7, you're done. Now they've also asked us to label each row, so I'm going to go ahead and do that. On the left hand side here, so row 7, row 6, row 5, row 4, all the way up to the top. And the first row, you notice you'll get to row 1 and you still have one more row left. That's because there's a row 0. And just to make that completely clear, beauty of a whiteboard marker is that I keep erasing my own work by accident. Alright, so you should have kind of a nice neat diagram like that one. And now what we need to do is look at number B. Says the powers of 2 can be found by looking for a pattern in the triangle. So what are the powers of 2? The powers of 2 are, well, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And just keep going for a few. And the question is, where do we find those values inside Pascal's triangle? I'll give you a minute to think about it. See if you can find that pattern. Not that pattern, see if you can identify the pattern by finding those numbers. Not all those numbers are explicitly in here, but you can make them somehow. Any guesses? Can I give you a big hint? Ready? This has something to do with row 0. This has something to do with row 1. This has something to do with row 2. This has something to do with row 3, and so on and so forth. What does the number 1 have to do with row 0? What does the number 2 have to do with row 1? What does the number 4 have to do with row 2? What does the number 8 have to do with row 3? Your brain should be trying different things. Should be multiplying, should be dividing, should be adding, should be subtracting. What is 1 plus 1? What is 1 plus 2 plus 1? What is 1 plus 3 plus 3 plus 1? See it? Okay. What is 1 plus 4 plus 6 plus 4 plus 1? And 1 plus 5 plus 10 plus 10 plus 5 plus 1. Okay? So this is the sum of terms in row 0. This guy is the sum of terms in row 1. This guy is the row 2. Row 3. And so on. Okay, so when we're talking about terms in Pascal's triangle, they can all be talked about in a certain way. They can all be represented by T sub n comma r, where n is the horizontal row number, that's here, and r is the diagonal row number, so that's here. Okay? So you see that there in front of you, and your diagram even has, although it's a bit tricky to see, it also has a little triangle off to the right with all of them named. So just to take a quick example, this top one here is the term that is in row 0, like the horizontal row 0 and diagonal row 0. Does that make sense? This next term over here that starts n equals 1, the first row, is in the horizontal row 1, but it's still in diagonal row 0. The next term is in horizontal row 1, diagonal row 1. Okay, the term that starts the next one is in horizontal row 2, still in diagonal row 0. The middle term is in horizontal row 2, diagonal row 1. And the next term is in horizontal row 2 still. It's 2 is going all the way across, but it's in diagonal row 2 as well. Okay? So you can start to see how the pattern forms even here. You've got the horizontal row first, which will go 0, 1, 2, 3, 4, 5, 6, except in a horizontal row, every first coordinate, you could call it, is the same. Right? 1, 1, 2, 2, 2, the next one will be 3, 3, 3, 3. But then the second term, second digit changes according to the diagonal row. Row 0, row 1, row 2. Okay. Each term is equal to the sum of the two terms immediately above it. We talked about that already. That can be represented as T sub n comma r is equal to T sub n minus 1 r minus 1 plus T sub n minus 1 r. So that basically means that you're looking at, to get the value of any term, you're looking at the horizontal row above it. So that's why it's n minus 1 in both of those terms of the addition there. And you're looking at the term just to the left of it and just to the right of it in the horizontal row above it. Okay, so that should make sense. Express T 5,3 and T 5,4 as a single term from Pascal's triangle in the form TNR. Okay, so any term in Pascal's triangle is the sum of the two terms immediately above it. So if we were looking for somewhere in this triangle, and I don't have the whole triangle drawn out for you, and I'm not going to draw the whole triangle out for you, but you've got the term 5,3 and you've got the term 5,4. What term is going to be directly underneath that? Well, it's in the next horizontal row. So what's its horizontal number going to be? 6. Okay. And based on what we saw, what's the value of r going to be? Is it going to be the same as this term, or is it going to be the same as this term? Is it going to be 3, or is it going to be 4? Basically what we're asking is this term that we're writing, is it going to be the third term in the row, or is it going to be the fourth term in the row? It's going to be the fourth term in the row. Okay? One easy way to think of that is the fact that we're making a pyramid here, right? So somewhere there's a line for the pyramid. You're going to have the diagonal term 2 and diagonal term 1 here and diagonal term 0. And this diagonal is going to come out here. And then the next row you're going to have 0, 1, 2, 3, 4. Okay? That's another way to think about it. Otherwise you can use the formula that they've given you and it becomes pretty straightforward. Okay? Again, just some trial and error. But the answer for the question there is T of 6, 4. Okay? Good. Okay, in your next example, example 3, there are more there are more patterns in Pascal's triangle. You have triangular dots. Okay, they represent triangular numbers. Write the number of dots under each diagram as a sequence. So you've got 1 in the first. How many in the second? 3. Then what? How many dots in the next? Thank you. 10. 10. Nice. Hey, how many dots do you think would be next if we drew another diagram? Don't draw the diagram. How many would be in the next one? How many would be in the next one? I hope some of you you're looking for this number right here. 28. Anyway, good job. Okay, so you don't need all those, but that's the answer for A. And you've already located these numbers in Pascal's triangle, but let's describe their position. What is their position? How would you describe their position? I guess rather than looking this way, could you also look this way? So where are these numbers? Row 2. Okay? They are in diagonal row 2. Okay. C says to write an explicit formula and a recursion formula for these triangular numbers. So we decided already that one of the best ways to write an explicit formula, and this is review now, is to develop a table of values and calculate finite differences. Okay, so I'm actually going to erase my Pascal's triangle. Hopefully I don't need it again. I probably will, but that's okay. You have your own. And we're going to just make a quick little chart here. And we're going to have the term number represented by n. Then we're going to have the term itself, so the value of the term, which we can record as f of n, the value of the function at n. And we're going to fill those guys out. So term number is the natural numbers, first term, second term, third term, fourth term. We can even go fifth term. And the value of the term is simply the term itself. So 1, 3, 6, 10, 15, and we could keep going, but we don't have to. Now to calculate the first difference, we're taking a y value, a value of the function, and subtracting the previous value. So the first difference is 3 minus 1, 2. 6 minus 3, 3. 10 minus 6, 4. 15 minus 10, 5. Do we have a constant first difference? No. What does that tell us so far? Yeah, we have to look for a second difference. Nice. Yeah, it's not a linear relationship. We could have figured out already, but so let's try our second differences. 3 minus 2, 1. 4 minus 3, 1. 5 minus 4, 1. What does that tell us? It is quadratic. Okay? So you're working on C here. You can say, therefore, quadratic. So let's start with a base quadratic function and see if we can figure out what the function is in order to get an explicit formula. Now we know that when we're dealing with quadratic, we're going to have the parameters a x squared plus bx plus c. Do we know the value of any of those numbers yet? And actually, sorry, I should have used the letter n because it's a function with respect to n, so not x. Do we know the value of a, b, or c yet? We do, if you did your homework from the first lesson. You should be aware that half the value of the second difference corresponds to the value of a. Okay? So if you don't know that, you just say, since a is half the value of the second difference, assuming the second difference is constant, and we know that this function with respect to n is, since the constant difference, the finite difference is 1, then we've got half n squared plus bn plus c. So we're getting a bit closer. How did we determine the values of b and c? Wasn't that long ago. So in order to determine the values of b and c, we needed two equations. So we're going to use this equation twice, and we're going to use two of these points in the equation, because each pair of numbers here will satisfy the equation. So let's use these two, and we'll create two equations. So if I put 1 in for y, there's that. And I'm going to put 1 in for n. Well, that's going to give me 1 squared is 1. That's going to give just 1/2 plus b plus c. Call that equation 1. And equation 2, I'm going to put in my other values. We're going to get 3 equals 2 squared is 4, and 1/2 of that is 2. And then we've got 2 times b, so we've got 2b plus c. That's my second formula. I'm going to go ahead and simplify them, reduce them. Yeah. Okay, so I have two equations, I have two variables. The only variables left are b and c. So I can simplify both of these equations a little bit by subtracting 1/2 from both sides in equation 1. Okay? So in equation 1, that's going to give me 1/2 equals b plus c. In equation 2, I can subtract 2 from both sides. That's going to give me 1 equals 2b plus c. Now I can use substitution or elimination. I am going to use elimination. I'm going to subtract these from each other because that will cancel out my c's. So it'll be, I subtracted 2 from both sides. I subtracted 2 from the right, subtracted 2 from the left. Okay, so now I've got half minus 1, that's going to give me negative 1/2. I've got b minus 2b, that's going to be negative b. And I got c minus c, that's going to be 0. So that tells me that b is equal to 1/2. And I'll just sub that into any one of my equations. If b equals 1/2, then c equals 0. Does that make sense? If b equals 1/2 and 1/2 equals 1/2 plus c, then c must be 0. So without doing the math on that, we're just going to give you that b equals 1/2 and c equals 0, which tells me that the explicit formula for the triangular numbers is f of n equals 1/2 n squared plus 1/2 n. Zoom back up here. Now, to develop a recursion formula, that means that we're getting a term by looking at its preceding terms. Well, we've actually kind of dealt with this already because we're really just looking at Pascal's triangle. And in order to do a recursion formula, we first need to give the first term. So f of 1 is what? 1, right? The first term is 1, second term is 3, third term is 6. How are we going to get the next term when we're starting with the first term? What did we add? That's where these first differences come into play. What did we add to the first term to get the second term? Okay, good. So to get the second term, we added 2. What did we do to get the third term? We added. What did we do to get the fourth term? Added 4. To get the fifth term, we added 5. Okay? So we're starting, if we want to find any term, we need to start with the term before it, and then add, what am I going to write here at the end? Where the term number is represented by n. We're not just adding 1, we're going to add n. Okay? So if you want term 5, you need to start with term 4 and add 5. If you want the next term, you're going to start with term 5, you're going to add 6, you'll get 21. Then you'll add 7, you'll get 28. Then you'll add 8, you'll get 30. Anyone else? 36? Okay, excellent. Good job. There's example 3. Okay, so powers of binomials can be expanded using patterns. One of the patterns for the coefficients is found in Pascal's triangle. And the pattern in the powers of a and b we discussed already, but now we're going to write them, okay? So you have just, maybe let's just do this. Let's say, make a little chart, and maybe watch, I don't know if you want to watch the chart first for a little bit, but we've got a plus b to the power of n, so we're working on expansions of a plus b, okay? When n is 0, a plus b to the power of 0 just equals 1, because anything to the power of 0 equals 1. Okay, when n is 1, we've got a plus b to the power of 1. Well, that equals a plus b. When n is 2, we've got a plus b to the power of 2. That's a plus 2ab plus, a squared plus 2ab plus b squared. When n is 3, that will give us a plus b to the power of 3. Okay, this one is a cubed plus 3a squared b plus 3ab squared plus b cubed. You know, the more you do this, the faster you get at it. In the fourth row, a plus b to the power of 4. And you should actually be able to think about your coefficients now. You know the patterns, and actually you know the patterns for the exponents as well. But we've got a to the power of 4 plus 4 a cubed b plus 6 a squared b squared plus 4 a b cubed plus b to the power of 4. We'll stop there. And we'll just make a note. One note is that the coefficients in the expansion of a plus b to the power of n can be found using Pascal's triangle. The powers of a begin at n and decrease by 1, while the powers of b begin at 0 and increase by 1s, or by 1. The last note about the powers, that the sum of exponents in each term is n. The sum of exponents in each term is n. So that means no matter what term you look at, let's just randomly pick this term here, the sum of its exponents is going to be 4 in every term in this row. Every term in this row, the sum of the exponents is going to be 3. Example 4, it is going to take the whole page-ish. We're going to expand those things using Pascal's triangle. So here we go. I'll do the first one with you. I'll probably just do them all with you. But I'll ask for help along the way. Okay, a plus b to the power of 7. Okay? And you can look back at Pascal's triangle. I'm going to need your help because I don't have it in front of me. Now I do. And since the exponent is 7, the coefficients come from row 7. Right? Okay, the powers of a will decrease from 7 to 0, and the powers of b will increase from 0 to 7. Okay? So I'm going to write it with all of the extra kind of information, and then we'll go through and cancel out the stuff we don't need. So the coefficient of the first term is 1. It's going to have a to the power of 7, b to the power of 0. Now you just need to pay attention. You need to pick the next number from row 7, which is 7. The exponent from a goes down 1, b goes up 1. Next coefficient from row 7. 21. A to the power of 5. B to the power of 2. Next coefficient. 35. Vlad, a to the power of... That's okay. 4. B to the power of... Good. Next coefficient. 35 again. Emma, a to the power of... B to the power of... Julia, next coefficient. Now we don't even need Pascal's triangle, you just look backwards. 21, a to the power of
2.
b to the power of Vlad. Next coefficient. Try not to copy, try to do it yourself.
So right. 7.
The next coefficient is 7, a to the power of
0 plus a.
1, a to the power of 1,
And 6.
and b to the power of 6. And the last term, coefficient of 1, no a's, so a to the power of 0, I am still going to write it, and b to the power of 7. Okie dokie. Yep, I'm going to do that in my next step. I'm just going to clean it up. Here all we need is a to the power of 7. Here we need 7 times a to the power of 6 times b. We don't need the exponent 1 because it is b to the power of 1 if it's not written. There's 1b there. Good. 21 a to the power of 5, b to the power of 2. You can also use this opportunity to double check that all the sums of your exponents should be 7. If not, you did it wrong. Alright. Should look like that.
Why'd you rewrite it?
I just rewrote it without the stuff that I didn't need.
You started reader.
Clean it up. Okay. Here we go. B. B is similar, but this time you have negative. So here's what's really important. The coefficients, so the exponent there on the expansion, m minus n is to the power of 5. So what row are we getting our coefficients from?
5.
Getting our coefficients from the 5th row. But we need to pay really close attention to that negative symbol. We're going to have, if you wanted to think about it this way, you could think about it as a plus b. But a here is m, and b is negative n. Okay, I'm not actually going to do that. I'm just going to think about it that way. So the first term is m, and the next term is negative n. So whatever we did with b here in the first round, we have to do that with negative n. Does that make sense? So when the exponent over negative n is odd, like negative n to the power of 1, it's going to make that whole term negative. But if it's even, like negative n squared, negative times negative is positive, the whole term is going to be positive. Okay? Let's see how it plays out. I'm again going to write out the step and then clean it up after. So the coefficient of the first term in row 5? 1. M to the power of 5, negative n to the power of 0. Now, it's negative n to the power of 0. Anything to the power of 0 is 1, even if it's a negative number. Okay, this is still just going to reduce to 1. Anyway, next term starts with 5. I keep writing a. M to the power of 4, negative n to the power of 1. Coefficient of the next term, row 5. 10. You guys don't have it memorized yet? M to the power of 3, negative n to the power of 2. Next coefficient is also 10, and my exponents are just going to kind of swap. M to the power of 2, negative n to the power of 3. Then I'm just looking back in my row. I know my next coefficient is going to be 5. Times m to the power of 1, negative n to the power of 4, plus 1 times m to the power of 0, which is just 1, negative n to the power of 5. Okay, let's clean this up. I don't need this 1 as a factor here because 1 times anything is just itself. This is also just 1, so I don't need that. So my first term is just m to the power of 5. In the next one, we have 5m to the power of 4. It's pretty straightforward. And we have one factor of negative n. So rather than leaving this plus sign here, the whole term is going to become negative because we have one negative factor. So we have negative 5 m to the power of 4 n. Okay? You see how the negative sign is no longer just with the n, because negative n got multiplied by the whole thing is negative. One negative factor. Okay, over here, it is positive because I have two negative factors. So I'm just going to have positive 10m cubed n squared. You say, what happened to the negative? Well, it got multiplied by itself, so it's now positive. All right? Now over here, we're going to have n cubed. Is it going to be positive or negative? Negative, which means I'm still going to have one negative factor, which means a negative times a positive times a positive. This whole term is going to be negative. Negative 10m squared n cubed. Is my next term going to be positive or negative? Positive. Positive 5m n to the power of 4. Is the next term going to be positive or negative? Negative. It's going to be negative n to the power of 5. So a bit of work, a bit cumbersome, but again, just being careful, following the pattern. Okay? The next one's going to be even a little bit more challenging. It's going to take up a little bit more space for us. It is 2x plus 1 to the power of 6. So which row of Pascal's triangle am I looking in for my coefficients? The 6th row. Okay, so the first coefficient is 1, and I'm going to have, pay attention, 2x to the power of 6 and 1 to the power of 0. That's just going to be 1, and we're going to be left with 2x to the power of 6, but you're going to see this exponent applies to the 2 and the x. Okay, we're not there yet, but that's what's going to happen, so don't rush ahead. Okay, the next coefficient is going to be 6. And then I have 2x to the power of 5. That's going to go down each time. And 1 is going to go up each time. Now you'll notice as we're doing this is, does it even matter if the exponent on 1 keeps going up? 1 to the power of 2, 1 to the power of 3, 1 to the power of 4, 1 to the power of 5. It's all going to be 1. But we'll keep writing it anyway for now. Next coefficient in row 6. Because we're running out of time, I'll just give it to you. It's 15. We've got 2x to the power of 4. We've got 1 to the power of 2. Next coefficient in that row is 20. We're going to have 2x to the power of 3. 1 to the power of 3. Now we know we're kind of like at the top of the mountain, right? As far as coefficients go, because our exponents are the same. So we're going back down the other side, which means our coefficient is 15. 2x to the power of 2. 1 to the power of 4. Next coefficient is 6. 2x to the power of 1. 1 to the power of 5. And we have room. Coefficient of 1. 2x to the power of 0. 1 to the power of 6. Is it all on there? Yeah, it is. Ish. Okay. Let's reduce that. So here, remember we said, this exponent, it's not 2 times x to the power of 6, it's 2 times x in that whole thing to the power of 6. So we need to know what 2 to the power of 6 is. 2, 4, 8, 16, 32, 64. Okay, so we've got 64 x to the power of 6. It's just times 1 and times 1. So 64 times x to the power of 6. 64x6. The next one is 2 to the power of 5, which is 32, times 6. Okay, that's going to give us 192 as our coefficient. And how many x's do we have?
5.
X to the power of 5. Now the next one, 2 and x are going to be raised to the power of 4. 2 to the power of 4 is 16 times 15. 15 times 15 is 225. So one more 15, 225 plus 15 is 240. So our coefficient here is 240. If you can't do that in your head, you do it on your calculator. X to the power of 4. This 1 to the power of 2 doesn't change anything. It's just multiplying by 1, which is itself. Okay, 2 to the power of 3 is 8. 8 times 20 is 160, and we have 3 factors of x. 2 to the power of 2 is 4, 4 times 15 is 60, and we have 2 factors of x. 2 to the power of 1 is 2, times 6 is 12, and 1 factor of x. And then we have 1 times 1 times 1, which is just 1. Now, when we took this binomial, yes, the pattern of Pascal's triangle still rings true here. But look what happened when we expanded and simplified. You can't even really tell where these numbers came from anymore. Okay, so you do need to be careful. You need to make sure you're doing it correctly. You need to follow the basic rules of algebra, and you should come out with the correct answer. Okay, one more really quickly. D. That was C. Change colors again. So that's the cool thing to do. D. We're looking at y over 2 minus y squared to the power of 4. So it's a little bit shorter, but also a little bit more complicated. The coefficients occur in row 4. And we're going to assume kind of A is y over 2, and B is negative y squared. Okay? Now, yeah. Y squared with a negative out in front of it. Let's see what happens. Coefficient 1. How many y over 2's? 4. How many of the other guy? 0. I'm not going to write it. Good. Next one. We're adding coefficient, row 4, so it's 4. Y over 2's, we're dropping down to 3. And now we're going to have 1 negative y squared. Next coefficient in row 4 is 6. We're going to have 2 factors of y over 2 and 2 factors of negative y squared. Next coefficient is 4. We're going to have 1 factor of y over 2. We're going to have 3 factors of negative y squared. Negative y squared in brackets to the exponent 3. And the last one has a coefficient of 1. And we've got negative y squared in brackets, and we've got 4 factors of that to the power of 4. Okay, let's reduce this thing and figure out what it all means. So here we are, this exponent applies to the numerator and the denominator. Okay, so you have y to the power of 4 over 2 to the power of 4. What's 2 to the power of 4?
32.
We need a tie break. 2, 4, 8, 16. Okay, so you got y to the power of 4 over 16. Done. Now this one has 1 negative factor, so it's going to be minus. And then you have y cubed over 8. So you can do this in multiple steps, but you've got, sorry, you're going to end up with 4 over 8. Okay? So you're going to have 2 in the bottom. Let's do it in multiple steps. Y cubed, so we got 4, y cubed over 8 times negative y squared. You can put that over 1 if it helps you think about it. And what's that going to reduce into? Well, we've got, oh boy, so and this isn't negative anymore because I already put the negative out front. Sorry about that. So we've got y cubed times y to the power of 2. That's y to the power of 5. And we've got 4 over 8. So this term, I'll rewrite my first term. This term is going to be y to the power of 5 over 2. Okay? Next term is going to be 6 times y squared over 4 times negative y squared squared is going to be positive y to the power of 4. Okay? So we've got 6 over 4, and it's positive. And then we have y squared and y to the power of 4. That's going to be y to the power of 6. Okay, you could put them in the numerator if that helps. That's what we were doing. The next term is right here. Okay, we've got these two don't really change, but they're going to be 4 over 2y. So this is going to be 2y, these two kind of combined. I'm just kind of not really organized, reducing it step by step, so just pay attention to the thought process. And then we have 3 factors of negative y squared. So that's going to be negative y to the power of 6. Yeah? So we've got a factor of y here and 6 factors of y here. So that's 7 factors of y. And we've got a negative times 2 positives. That whole term is going to be negative. We've got negative 2y to the power of 7. And the last term over here was just negative y squared to the power of 4, which is an even number of negative factors. So it's going to be positive, and it's a power of powers law. So I multiply my exponents. It's going to be y to the power of 8, which can just come right down here. Positive y to the power of 8. There you have it. Use your patterns, be careful, use Pascal's triangle, exponents increase and decrease by 1 respectively, and pay close attention to what you're doing in the algebra. Your practice problems are from page 378, number 1 through 10.
So we can